Hi everybody, this is Mrs. Ellsworth, and we're going to be discussing gases, the behavior of gases, so that we can talk about the gas laws. You guys have had a small introduction about the gas laws when you did the PhET lab simulation last week, but now we're going to talk about pretty much their behaviors, and so it can explain some phenomena that occurs. Okay, so here we go. So what we're going to do today, our goals are to describe the kinetic molecular model or kinetic molecular theory of gases. And we're also going to go over a little bit about pressure, and then this part will be left for another time. Okay, so here we go. So gases are usually colorless, but have several do have color, like chlorine is a greenish yellow color, and nitrogen dioxide is a reddish brown color. Gases can be fragrant, and I'm sure that lots of you who drive around the road here in Minnesota that you can recognize that this is, oh, you know what it is. Anyways, this stinks bad when they spread manure. Anyway, so there's that, and then also they can be fragrant. It can stink like a skunk. Here's something that's fragrant. Okay, just even looking at it kind of makes you think, well, what does that smell like? And unfortunately, I have been sprayed by one of these a couple years back in our barn. I got sprayed by one, and that smell gets stronger as time goes until a certain point. It's terrible. Anyway, I digress. Let's move on. And then also you can think about other things that smell too. And so like fresh mint, that's got another. Anyway, so if you can smell it, it's a gas. Okay, gas molecules are coming from whatever source it is, and they are coming to your nose, and your nose is able to receive them and from receptors. Okay, so moving on. Okay, so we're going to talk about 6 different properties of gases. Okay, and then we'll talk about that'll help explain the kinetic molecular theory too. Okay, gases have mass. If you go and you deflate a balloon and you measure it when it's full, and you measure the mass of it when it's empty, they do have slight difference in mass. You know that it's not a great amount, but there is a difference in mass. The density of gases are much less than they are when they're in liquid or solid form, because they aren't packed close together at all. And the warmer that it is, the more that it expands, the less dense that it is. So it's a very compressible type of matters, where liquid and solids aren't, because they are so closely packed. Oh, and here I jumped ahead. Gases are also compressible. We can go and buy propane in a compressed gas tank. And then you can think about it too, that if you were going to sit on one of those exercise balls, okay, you can compress it by sitting on it, compress a balloon by sitting on top of it, and hopefully it doesn't break. But anyway, so they can be compressible. So we really cannot measure their volume unless we figure out a specific way, because this compressible problem is a problem for measuring volume. Okay, they also fill their containers completely. The gas molecules go evenly all throughout, and they fill up the container. And so I moved on to this one. Gases can move through each other quite rapidly, so they can pass each other rapidly, or else they can bounce off each other. They can diffuse through a whole area. So if you even think about diffusion, okay, think about somebody who has opened a container of something that's stinky, or somebody has passed gas. I mean, it diffuses through the air. You can smell it from afar because gas spreads out. It spreads out evenly throughout a whole area. You know, they used to always talk about those pumps that you can buy to put on top of a 2-liter pop bottle, and that you can pump it up after you've drank some out of this 2-liter pop bottle, that you can pump it up so that you can save the carbonation and keep it fresh. But it doesn't matter, because it has to be carbon dioxide that's in the air portion of that bottle, because it's the carbon dioxide that will stay diffused through in and out of the pop solution. But if you put in nitrogen and oxygen from the air, that doesn't matter because the gases diffuse and they mix evenly. It has to be that equal pressure, equal amounts of carbon dioxide above the liquid and below the liquid. So those pumps that they buy for are really quite a gimmick. Anyway, gases diffuse, they mix, they move through each other, and they mix quite well. And they will be evenly distributed all throughout too. Now, gas also produces pressure. Okay, if you've ever went down a steep hill, steeper than most Minnesota ones, you'll notice that you have to pop your ears because the pressure of this being put on your eardrum. You need to equalize the pressure by popping your ears, by chewing gum or yawning or something. You can also inflate balloons. The further and further and further that you blow that balloon out, the stronger that the pressure is, because the pressure outside is also exerting force on it too. Tire pressure. Okay, we fill it up. We know we can measure that pressure, can't we? Anyways, pressure is talking about these molecules that are moving fast, and they are exerting pressure by bouncing onto the outside of the container. Okay, so pressure of gas depends on temperature. So you notice that we were talking about tires up here, tires down here too. I have a vehicle that tells me what the pressure in my tires is. When it was very cold in Minnesota winter, they were down to 32, and it was telling me I had to go and fill them up. I did. And then I noticed just a couple months later, they're up at 36, 37, and I have to let some out here as soon as it gets a little bit warmer. Or if I drive very far, I'll have to let some out because the pressure changes with the temperature. It's high temperatures, got high pressure. Low temperatures, you got low pressure. I also think about this too. Have you ever gotten one of those Mylar balloons? And then you have to go out in the winter and go take them somewhere. And when you take them outside in Minnesota, January, they deflate, it looks like. And so you feel deflated yourself when you see it, and then you take it back into warm space and they're inflated again. That's because the gas molecules move closer together when they're cold. They move further apart when they're warm. You probably recognize some of that from that PhET lab simulation that you did. Okay, so here let's look at a kinetic molecular model, or for the kinetic molecular theory. Okay, so the first idea here, this is an assumption that all gases consist of small particles that have mass. When we're in physics, we call these a point mass, and so we do some information with that, but they all have constant random motion. In fact, this random motion, we call it Brownian motion, and it exerts pressure on the containers by bouncing onto the outside of the container. Okay, we also assume that the gases are separated and far apart from each other. They bounce off each other, and these point particles, their volume is negligible because they're so small and they're moving very fast. So the volume is it's a problem for measuring with gases. The third one, we assume that gas must be in constant rapid motion and it easily mixes, except for when it's colliding. Sometimes the particles, when they collide, that they will connect, but that usually doesn't happen because gases are moving so fast that they won't. And they are all in straight line motion. Gravity does not affect anything there. It is just going in straight line, constant rapid motion. Again, random motion, that was created by Einstein, that the term was, but it describes a random motion. Okay, and then the fourth assumption that we have is that gases exert pressure because the particles frequently collide with the container. Okay, and the more collisions, the more pressure that has on there. So that is directly proportional to how fast they're moving, which has something to do with temperature, doesn't it? So all these things kind of come together. Now, on the next page here, I've got a couple of animations. Okay, so here's an animation of a gas particle that is in other gas particles, and that's talking about Brownian motion, just random wild motion with no influences on anything except for when they're bouncing into each other. Okay, the next one from that, let me get it here real quick, is this one, and I think this one is excellent. These are blue particles representing that they're cold. And so what are they going to do? They're going to exert some pressure on there. Now they're turning purple, and now they are red, and look how fast that they are moving. So the more pressure that we exert on them, the hotter they became, and the faster that the motion became. And then now it's just going to go backwards. And they're actually blue again. Okay, so let's see, one last slide here. So finally, the kinetic molecular theory, the models of these, they help explain why temperature and pressure are directly proportional. They also help explain the gas laws. When you think of gases, you have to always think of that random motion that goes as fast, depending on the temperature, as possible, moving and hitting collisions on the outside of the container. Okay, so that's the kinetic molecular theory of gases, and that will help explain our ideal gas laws for tomorrow. Talk to you later. Bye-bye.